When you look at a modern container ship, you're seeing a literal floating city of steel. It's a symbol of incredible strength. But deep within that steel, there's a hidden battle going on, a constant fight against invisible forces that can bring these giants to their knees. So today, we're going to uncover the unseen flaws of these massive steel structures.
So why do these giants of the sea actually fail? It's a huge question, one that keeps naval architects and marine surveyors up at night. And the answer isn't always some dramatic storm or a sudden collision. A lot of the time, it's a slow, creeping failure that starts at a level you can't even see. So let's put on our detective hats and really investigate the hidden culprits behind these catastrophic failures.
And right here, this is the key to our whole investigation. We're not looking for a single smoking gun. Instead, we're hunting for signs of gradual wear, tiny flaws in the design, and the just relentless pressure of the ocean. Understanding these invisible enemies is absolutely crucial to keeping these vital arteries of global trade flowing safely.
Okay, so to solve this mystery, first things first, we have to identify our suspects. Luckily for us, marine surveyors have already created a kind of profile for them, grouping them into a few key categories. And that gives us the perfect roadmap for our investigation.
All right, you've got your sudden, really dramatic stuff, like a collision or running aground. Then you have the problems that were literally built into the ship from day one. Bad welds, poor design. But it's these slow killers that are often the most insidious, fatigue and corrosion, working away silently over decades. Let's take a closer look at those two.
The best way to think about fatigue is with a simple paper clip. You can bend it once, no problem, but bend it back and forth in the exact same spot over and over again, and what happens? It snaps. A ship's hull is doing that all the time, constantly flexing and bending in the waves, and those tiny repeated stresses over and over thousands of times, that's what starts these tiny little cracks that can grow into something much, much worse.
So while fatigue is busy weakening the steel from the inside, you've got corrosion just eating it away. And one of the nastiest forms is called pitting. Instead of a nice, uniform layer of rust, it creates these deep, tiny holes. In each one of those pits, it's like a little weak spot, just a perfect starting point for a brand new crack.
Now, this is where things get really scary. See, these two, fatigue and corrosion, they don't work alone. They're a team. The areas with high stress, the exact places that are most vulnerable to fatigue, also happen to be the places that corrode the fastest. So you get this vicious cycle, this runaway feedback loop of failure. The corrosion weakens an area, which puts even more stress on the steel that's left, which then makes the corrosion happen even faster.
All right, so if stress is the main villain in our story, we need to figure out where it likes to hide. Let's zoom right in and really dissect the anatomy of a crack to see how a seemingly minor choice in the design can create a deadly hotspot just waiting for a failure. Think about the way stress flows through steel. It's a lot like water flowing in a river. If the riverbank is nice and smooth, the water just flows evenly. But if you have a big, sharp rock sticking out, the water swirls and gets violent right around it. Well, a stress concentration, that's the sharp rock. It's any abrupt change in a ship's structure that basically forces all that stress to pile up in one tiny area.
Okay, time to put our detective hats back on. We're going to investigate a classic example of a stress concentration. It's called a hardpoint, and it's one of the most common reasons for cracks that inspectors find on ships.
So here's the story of how this happens. You've got this really rigid bracket, right? And it's welded to a big, flexible steel plate. But here's the problem. The bracket just stops right in the middle of nowhere. So when that big plate flexes with the waves, all the stress gets funneled right to the very tip of that stiff bracket. That's your hard point. And almost inevitably, a crack starts right there. But check this out. The solution is actually brilliant because it's so simple. You just extend the bracket so it reaches the next structural support. Now the change from rigid to flexible is gradual. The stress can flow smoothly, just like water in a nice, smooth channel.
Okay, just a super quick clarification here. A hard point failure is when the plate next to the bracket cracks. An end of bracket failure is when the bracket itself, or its weld, is what breaks. They're two different problems, but you often find them in the exact same spots.
Okay, so finding the problem is half the battle, but fixing it, that's a whole other story. And this is where things get really, really clever, because the right way to repair something depends entirely on the context, especially how old the ship is.
So let me ask you this. If you find the exact same crack on a ship that's 2 years old and on another ship that's 20 years old, does it mean the same thing? And the answer? Absolutely not.
This is just a fascinating look into the biography of a ship, really. See, a crack on a brand new ship, that's a massive red flag.
It means the stress in that area is way higher than it should be. It's a clear signal of a flaw in the design or the construction. The whole area needs a redesign. But what if that exact same crack shows up after, say, 20 years? Well, that actually tells you the design was pretty good. It just reached the end of its life. So in that case, a simple repair back to the original standard is usually the right call.
And when you're dealing with corrosion, the decisions are just as calculated. It's not guesswork at all. Surveyors have very specific rules. If the pitting is pretty shallow, you can repair it with epoxy or welding. But once it crosses a certain line, like if the pits are deeper than half the plate's original thickness, or if they cover more than 30% of the area, then it's a no-brainer. You're not patching that. The entire plate has to be cut out and replaced.
And this brings us to what is pretty much the golden rule of any repair. You can't just slap a weld over a crack and call it a day. A weld itself can create a new point of high stress. A proper repair means cutting out the bad section and putting in a new piece of plate, making sure the new welds are in places with low stress. Because get this, a bad repair can actually be worse than the original problem.
All right, so we've been deep in the weeds here, looking at the microscopic world of cracks and rust. Let's pull way back for a second and ask the big question. Why does any of this meticulous work actually matter?
Well, it matters because the stakes could not possibly be higher. A single failure in a ship's hull can cause a massive environmental disaster, it can disrupt the entire global supply chain we all depend on, and most importantly, it puts the lives of the crew in danger. This invisible shield of steel and all the hard work that goes into maintaining it, it is the absolute, unseen bedrock of our modern world.
You know, at the end of the day, maintaining a ship's hull is a job that is never, ever finished. It's this constant, dynamic struggle. It's like this constant, high-stakes chess match between human engineering and the relentless, powerful forces of nature. And that really leaves us with a fascinating final thought. As we keep developing new materials, smarter sensors, and better designs, how are we going to tip the scales in this constant battle? What kind of innovations will define the next generation of these unstoppable steel giants?